Okay, here's the presentation of Project 1 we did. This is group Borao and Qianyun Zhu. So I'm Qianyun Zhu and I did the algorithm 2 part, so I'll be talking about the first part, which is algorithm 2, and then we'll be talking about the Fox algorithm. So in my implementation, the matrices are stored in one-dimensional arrays using the row major order. The global variables are matrix A, B, and C. A and B are the matrices that are going to be multiplied. C is the result matrix we're going to get. And I've also defined two other matrices just to make the calculation easier. One is matrix B in column major order, and the other is C in column major order. The local variables are local A, which is only a chunk of matrix A assigned to each processes, as shown in the red rectangle. Local B is the same. The only difference is that the chunk is sliced by column. Local C is the result of a local A multiplied by a local B, as shown in the red rectangle. Local C all is the aggregation of all the local C's calculated in the process. The basic idea of this program is to calculate local C first, then put each local C into the correct position in local C all, then aggregate all local C alls to get our final matrix C. Here's a step-by-step. The first step is pretty straightforward, generating random matrix A and B. Step 2 is scatter matrix A and B to all processes. Scattering matrix A is pretty straightforward, but scattering matrix B is a little bit more complicated since we need to split it by column. So here we transpose matrix B to get its column major order representation, which is stored in the matrix B column major variable, and scatter that. Step C, we calculate local C using local A and local B using the matrix multiplication formula. And in step 4, here is an illustration. Take process number 2, for example. In this iteration, we already calculated row 2 by column 2, which is stored in variable local C as shown in the orange rectangle. And what we do in this step is to store it in the proper location of location C all variable. And you can see that it is stored as the second chunk in local C all, as shown in the yellow rectangle. After doing a number of iterations, we'll get the full local C all. And please note that in order to combine all the local C all slices to get our final result, each local C all matrices is stored in column major order format so that our next gathering step would be easier. In step 6, we rotate local A, then repeat step 3 through 5 until local A is back to its original position. And the rotation of local A is achieved through using MPI send and receive replace function, which prevents deadlock and is very simple to use. In step 7, we gather local C alls from all processes and get the matrix C in column major order. In step 8, we get the final result, matrix C, from matrix C column major order by doing a simple matrix transpose. And here's the performance of algorithm 2 under our implementation. The time increases exponentially as the size of matrices grows. The time used for matrix multiplication is reduced by adding the number of processes. And here's efficiency table, and following the red line, we can see that algorithm 2 can maintain an approximate constant efficiency if the problem size increases at the same time as the number of processes increases, which proves that this algorithm is weakly scalable.
Now let's talk about Fox algorithm implemented by Borao. First, let's look at the global variable and local variable. To compute C equal to A multiplied by B, matrix A and B is divided into blocks. The number of blocks is equal to the number of processors. See the picture as example of 9 processors. The matrix A is stored in total matrix A, and so as matrix B. Our goal is to compute the total result equal to total matrix A multiplied by total matrix B. We will do it in parallel by multiprocessors in local variables. The local variable block result equal to the block A multiplied by block B, and the block A and block B will change in each step. Then the result in each step will be connected and compute the block of total result. Each matrix and blocks is stored in one-dimensional array by row major order. There is a formula for contribution matrix B into blocks by the coordinate of each block, where the block length is the length of the block, which the block is a square matrix, and the matrix length is the length of matrix. Block X and block Y is the coordinate of the block. The first step, the matrix B has already been distributed to each process by order as block B. Firstly, we broadcast the AII block to processors in row I as block A. Then we multiply block A and block B. Third, we send the block B to the process directly above and receive from the process directly below as new block B. There is an example by 9 processors. Then in the JS step, we broadcast AII plus J mod N blocks to processors in row I as block A, which n equal to the square root of number of processors. Then we multiply block A and block B. Third, we send the block B to the process directly above and receive from the process directly below as new block B. Then we repeat the step in n times. We will get the result block in each process, as is shown example in 9 processes. There is some detail of implementation in code. Firstly, the broadcast block of A. We first should check if the sending block A and the destination process match. And we can't use broadcast function. We have to use send and receive to send block to specific processors. The multiplication result. The result is also a block, so it's a one-dimensional array of integer, which is in row major order. We will store and add each result in each step to get the final result of the block, which is of the result matrix C. In sending and receiving block B, we should find the process rank by the coordinate of process block, and then we use send receive function to prevent deadlock. In sending back results, we use gather to get the block result to total result, but the order will be wrong. There is a formula to reorder the total result by blocks. Then let's look at the result of the Fox algorithm. First, this is the time consumed in Fox algorithms. Then it's speed up and the efficiency. We can look at the efficiency drops very quickly when the number of processors is more than 16. Because the algorithm can be implemented totally by collective communication, such as gather and scatter. So, because some steps, such as broadcasting block A and exchanging block B, can be implemented by the connective communication function. So the running time will increase in big O n rather than big O log n. The efficiency can hold with the increasing of process number and the data size. So the Fox algorithm is neither strongly scalable nor weakly scalable. Thank you.